Okay, good morning. Welcome to
FamilyMath790.
FamilyMath790. So today is sort of a combination of a project I did with versions of with each one of you individually. But what I'm going to look at is those are supposed to be the same size and they're supposed to fill the square. We're going to look at packing circles in a square today. And we did the Robert Kaplinski project together where you had pipes stacked.
Yep.
Remember that? And then you and I did the Iowa State problem where you had circles in an equilateral triangle.
Mm-hmm.
Okay, so we're going to combine those two problems. So first we're going to look at the pipes stacked on top of each other like this. And then what we're going to do is let the number of circles go to infinity. So go to infinity, get really large. So we're packing as many in as we can.
Alright.
Like this. And my question to you first is, what do you think is going to happen to the area of the circles as we let those circles go to infinity? So we're going to have, this many circles that way, this many circles up like that.
I think the area is going to actually approach 0.
Oh, okay. Yeah, the total area of the circles. Just to be clear, not just the area of one circle, the area of all the circles together.
So wouldn't it fill the square entirely?
Okay.
So whatever the area of the square is.
Okay. So if it was a 1 by 1 square, you would say it was just going to go to 1.
Yep.
All right. Now you've done a version of this project, so you probably have a different idea. What do you think is going to happen?
So I think the area of the circle, it's going to approach a value, but it won't ever get as big as the whole square.
Okay. Alright, so it sure seems like, especially when I draw these small circles, if they filled in, it sure seems like we're going to hit all the area.
Yep.
Let's see what happens. Where do you think would be a good place to start on this?
Maybe with just a one circle.
Okay. Alright, so actually for simplicity, instead of choosing a 1 by 1 square, I think I'm going to choose a 2 by 2 square.
Alright.
Alright.
Just to make it easier in the first round. Okay, so I've got a 2 by 2 square here. Can you tell me the area of this circle here?
It's going to be pi.
Alright, how'd you figure that out?
So the radius is 1, and then it's just pi r squared, which is pi.
Okay, great. So with one circle, we get pi, and so...
Then out of 4.
Yeah, so with one circle we got pi out of 4, so we could, if we want to keep track of the ratio, it's pi over 4. Okay, I guess the next stage would be 4 circles, right?
Yeah.
As we had before. I'm interested to see, maybe you can tell me in this case too. Looks like we'll have it divided up like that. What's the total area of these circles here?
So you have this radius is 1/2 here. So it's going to be a 4th pi for each of these circles. So it's going to be pi.
Whoa. 4, we get pi again. So out of 4. Alright. What do you think it's going to be with 9?
Maybe pi over 4 again.
Alright, why?
Because, yeah.
Go ahead.
Okay, so you can see we have this 1 going into 4 again in each of these small squares. And we know from our first example that that's going to leave it with this, it's going to have the same area. So the 4 smaller circles in this circle are going to have, or square, are going to have the same area
Okay.
as this one big circle. So it's going to leave us with the same overall area.
Okay, that's not the 9 case though. What case is that?
That's the 16 case.
Alright, that's the 16 case. So for 16 we get pi over 4. But that's fine. What sequence could you follow then to get the limit here using that method?
So you maybe use.
So it would just be 2 to the n.
Okay. And you see that you always get the same answer.
Yep.
Pi over 4.
Surprise.
Yeah, it is a surprise. And pi over 4 is, well, we can look at it on the calculator.
Be
That's the ratio of the area to the circle area to the whole area.
Yeah, so our area was 4 of the square. It's divided by 4, so that probably wasn't right.
Usually 10, that was 10 pi.
Divided by 4.
so 0.78.
Yeah, so a little bit more than 3/4 of the area is taken up. And the interesting thing is when you stack this way, you always take up that's the same amount of area.
Interesting.
Yeah, it's a little bit of a surprise that you don't fill the whole area. But now we're going to do the what was it? They're kind of called staggered. The staggered stacking, which is going to be a little bit harder of a problem. A little bit, tiny bit harder.
All right.
Let's take a look.